The Sun feels enormous, a burning sphere so massive it holds the entire solar system together. More than 1 million Earths could fit inside it. Its gravity controls planets, asteroids, comets, and worlds billions of kilometers away. But in the universe, the Sun is not a giant, not even close, because far beyond our solar system, there are stars so large they make the Sun look almost tiny. Stars swollen near the ends of their lives. Stars so vast that if they replaced the Sun, they could swallow Mercury, Venus, Earth, Mars, Jupiter, and keep going. These are red supergiants, some of the largest stars ever discovered. But one star may push the limit even further, a distant, dust-hidden monster known as Stephenson 218, a star estimated to be more than 2,000 times wider than the Sun in radius, so large that if it sat at the centre of our solar system, its outer layers could reach towards Saturn, a single star large enough to bury most of the solar system inside its atmosphere. And yet, this star is difficult to measure, unstable, obscured by dust, and so extreme that scientists are still cautious about what it really is. So before we go deeper, subscribe. Because this is not just a video about one of the biggest stars ever found. It is a story about scale beyond human instinct. About a star that makes the Sun feel small. A giant that may sit near the limit of what stars can become. And a reminder that the universe can build objects so enormous, they almost should not exist. Before we can understand a star like Stephenson 218, we have to start with the star we know best, the Sun, because the Sun already feels impossibly large. It dominates our solar system. It contains almost all the mass in it, more than the planets, the moons, the asteroids, the comets, and everything else orbiting around it, all combined. Earth feels huge to us, a world of oceans, continents, mountains, storms, and billions of lives. But beside the Sun, Earth is almost invisible, a tiny sphere moving around a fire so large that more than 1 million Earths could fit inside it, and even that does not fully capture the scale. The Sun is about 1.39 million kilometers wide, a distance so large that if Earth were placed across its face, it would look like a small dot against a blazing surface. The Sun's gravity reaches across billions of kilometers, holding Mercury close, guiding Earth through its orbit, pulling on Jupiter, shaping comets far out in the dark. Even Neptune, the most distant major planet, remains bound to the Sun's influence. That is how powerful it is. One star, sitting at the center of everything familiar, controlling the motion of worlds across the solar system. And yet, the Sun is ordinary. That is the strange part. To us, it is everything. But to the universe, it is a fairly normal star. Not tiny, not gigantic, not unusual enough to stand out among the galaxy's hundreds of billions of stars. It is stable, middle-aged, long-lived, and calm compared to the monsters that exist elsewhere. The Sun is not one of the largest stars. It is not one of the brightest. It is not one of the most massive. It is not near the limits of what a star can become. And that is where scale begins to break. Because if something as enormous as the Sun is considered ordinary, then the largest stars must be almost beyond imagination. There are stars with radii hundreds of times larger than the Sun. Stars so swollen that their outer layers stretch across distances wider than entire planetary orbits. Stars so luminous they release more energy in a moment than the Sun produces in days. Stars living fast, burning violently, and approaching the final stages of their lives. The Sun gives us warmth. It gives Earth stability. It burns slowly enough to last for billions of years. But massive stars are different. They spend their fuel quickly, they grow unstable, they expand into giants, and some become so large that the solar system itself becomes the only useful comparison. That is why starting with the Sun matters, because it gives us a scale our minds can almost hold. A star big enough to contain more than 1 million Earths. A star strong enough to rule over planets billions of kilometers away. A star bright enough to power almost every living thing on our world. And still, compared to Stephenson 218, the Sun is small, not slightly smaller, not modestly smaller, but almost absurdly smaller, like comparing a spark to a burning continent, a familiar star to something that stretches across the scale of planetary orbits. And once you understand that, the real question becomes unavoidable. How does any star grow that large? How does a burning sphere of plasma expand until it becomes larger than the space between worlds? And why do some stars become giants near the end of their lives? A star does not become enormous by accident. It grows because the balance inside it begins to change. For most of its life, a star is caught between two forces, gravity pulling inward and pressure pushing outward. Gravity tries to crush the star into itself, while nuclear fusion in the core releases energy, creating heat and pressure that push back against collapse. For a stable star like the Sun, this balance can last for billions of years. Gravity pulls, fusion pushes, and the star remains steady. But stars do not have unlimited fuel. Deep in their cores, they are burning hydrogen, turning it into helium, releasing the energy that makes them shine. And eventually, that hydrogen begins to run out. When this happens, the star's core changes, the balance weakens, gravity begins to squeeze the center more tightly, the core heats up, new layers of fusion can begin around it, and the outer parts of the star start to expand. The star grows larger, cooler on the surface, redder in color, and far more unstable. This is how stars become giants. They are not simply getting bigger like balloons filled with air. They are entering a new stage of life, a stage where the core and the outer layers no longer behave the way they once did. The inside contracts, the outside expands, and the star begins to swell across space. For a star like the Sun, this future will eventually turn it into a red giant. Billions of years from now, the Sun's outer layers will expand, possibly swallowing the inner planets, changing the solar system forever. But the larger stars go much further, because they begin with far more mass. They burn brighter, live faster, and die younger. A massive star may shine with incredible power, but that power comes at a cost. It burns through its fuel at a terrifying rate. What the Sun spends slowly over billions of years, a massive star can burn through in only millions. And when those stars reach the later stages of their lives, their outer layers can inflate to extraordinary sizes. They become red supergiants, stars so wide that their surfaces stretch far beyond the scale of ordinary stars. Their cores are intensely active. Their outer atmospheres are huge and unstable. Material can rise, fall, pulse, escape, and surround the star in dust and gas. These stars are not calm spheres. They are unstable giants, burning through the last chapters of their lives. Their surfaces may be cool compared with smaller blue or white stars, but their size makes them incredibly luminous. A red supergiant can shine with enormous power simply because its surface area is so vast. Even if the surface is cooler, there is so much surface-releasing light that the total energy becomes immense. That is what makes them so strange. They are cool and red on the outside, but violent and extreme underneath. Their cores are building heavier elements. Their outer layers are swollen almost beyond belief, and their futures are unstable, because a star this massive cannot keep balancing itself forever. Each stage of fusion creates new pressure for a time, but eventually the fuel runs out again, the core changes again, the star struggles again, and the giant becomes closer to its final collapse. This is why the largest stars are often stars near the end. They are not long-lasting peaceful objects. They are temporary extremes, huge because they are unstable, bright because they are burning through their remaining fuel, and dangerous because their final death may be one of the most powerful explosions in the universe. But before we reach that ending, we have to understand just how large these giants can become. Because before Stephenson 218 became famous, there were other stars that already seemed impossible. Stars so large that they made the sun look like a spark. And for years, one name stood near the top of the list: Uiscuti. Before Stephenson 2-18, there were already stars that seemed too large to be real. Stars so enormous that the sun stopped feeling like a star and started feeling like a tiny point of light beside them. One of the most famous is Betelgeuse, a red supergiant in the constellation Orion, visible to the naked eye. A star humans have watched for centuries without realizing just how extreme it truly is. Betelgeuse is already enormous, so large that if it replaced the Sun, its outer layers could reach far beyond the orbit of Mars, maybe even toward the asteroid belt depending on its exact size. Earth would not orbit beside it. Earth would be inside it. The familiar inner solar system would vanish beneath its swollen atmosphere. And yet Betelgeuse is not even the largest star we know. It is only the beginning of the scale problem. Then there is VY Canis Majoris, another red hypergiant, a star so vast and unstable that it has thrown huge amounts of material into space around itself. Its outer layers are not calm. They are messy, expanding, erupting, surrounded by clouds of gas and dust, like a dying star already beginning to fall apart before its final explosion. For years, VY Canis Majoris was treated as one of the largest known stars, a monster large enough to make the Sun seem almost insignificant. But even that was not the final step, because another name became famous for its size: Uiscuti, a red supergiant so large that it became one of the most widely known giants in astronomy. For a long time, Uiscuti was described as possibly the largest known star, a star with a radius hundreds or even over 1,000 times larger than the Sun's. If placed at the centre of our solar system, its surface could stretch far beyond Earth, far beyond Mars, and deep into the region of the outer planets. The numbers become almost meaningless, because once a star becomes larger than planetary orbits, the human mind has nothing normal left to compare it with. A star is supposed to be something planets orbit, but with these giants, a star becomes large enough to swallow the places where planets should be. The solar system becomes a measuring tool. Mercury becomes nothing. Venus becomes nothing. Earth becomes nothing. Mars becomes nothing. Even Jupiter begins to feel close. That is what red supergiants do to scale. They break it. They turn the Sun from the centre of our world into a tiny comparison point, and they show that the universe can build stars far larger than anything our daily experience prepares us for. But there is a problem. Measuring stars like this is extremely difficult. They are distant. They are surrounded by dust. Their surfaces are not sharp like solid planets. Their outer layers can expand, pulse, and throw material into space, so the numbers can change. A star once believed to be the largest may later be revised. Its distance may be updated. Its temperature may be recalculated. Its radius may shrink or grow in new studies. That is why the title of largest star is not always permanent. It depends on measurement, models, dust, brightness, and uncertainty. Betelgeuse shocked us. VY Canis Majoris pushed the scale further. Uiscuti became the famous giant. But then scientists studied Stephenson 2-18, a star that may surpass them all, a star so large that even the usual giants begin to feel smaller, a star whose estimated size reaches into a realm that is difficult to explain, because if the measurements are even close, Stephenson 218 is not just bigger than the Sun, it is bigger than the stars we already use to define impossible, and that is when the story becomes truly unsettling. Because the question is no longer whether giant stars exist. We know they do. The question is how a star can become this large, and whether Stephenson 2-18 is showing us the upper limit of what a star can be. Then we reach Stephenson 218, a star so large that even among giants, it stands apart, hidden deep in the Milky Way. In a distant region filled with dust, gas, and massive stars, Stephenson 218 is not something you can simply look at and understand. It is far away, obscured, difficult to measure, and surrounded by uncertainty. But if the best estimates are close, then this star may be one of the largest ever discovered. Its radius has been estimated at around 2,150 times the radius of the Sun. Not twice the Sun, not 10 times, not 100 times, more than 2,000 times wider in radius. And that number changes everything, because radius is not volume. When a star's radius becomes 2,000 times larger, its total volume becomes almost impossible to picture. Stephenson 2-18 could fit roughly 10 billion suns inside it. 10 billion. The Sun already contains more than 1 million Earths, and this star could contain billions of suns. Compared with Earth, the number becomes almost meaningless. Around 13 quadrillion Earths could fit inside a volume that large. 13 quadrillion worlds inside one star. That is the scale we're dealing with. A star so enormous that ordinary comparisons collapse. So the only way to imagine it is to place it where the Sun is, at the center of our solar system. If Stephenson 218 replaced the Sun, Mercury would vanish inside it, Venus would vanish, Earth would vanish, Mars would vanish, the asteroid belt would disappear, Jupiter would be swallowed, and the star would keep going, out beyond Saturn's orbit. The solar system we know, the one that feels so vast, would become buried inside a single stellar atmosphere. Earth would not be close to its surface. Earth would be deep inside the star itself. The planets would not orbit around it. They would be consumed by it. And Saturn, a world so distant that sunlight already feels weak there, would sit near the scale of its outer edge. That is what makes Stephenson 2-18 so unsettling. It turns the solar system into a comparison chart. It makes the Sun feel like a spark. It makes planetary orbits feel small. And it shows that a star can become so inflated, so extreme, so physically vast, that the distances between worlds no longer feel large enough. But this is not a calm object. A star this huge is not stable in the way the Sun is stable. It is a red supergiant, a late-stage star with swollen outer layers, a star losing material into space, a star surrounded by dust and uncertainty. Its surface is not a hard boundary, not a solid edge, but a vast, unstable outer atmosphere, expanding, moving, changing, making the star even harder to define. So when scientists estimate its size, they are not measuring a clean sphere like a planet. They are studying light, temperature, distance, brightness, dust, and models, trying to understand how large this impossible object really is. That is why Stephenson 2-18 is both amazing and difficult. It may be the largest known star, or one of the largest, but the exact number is uncertain, because the farther and dustier a star is, the harder it becomes to know its true size. Still, even with uncertainty, Stephenson 2-18 remains one of the most extreme stars ever studied, a giant among giants, a star so vast it forces us to stretch the solar system around it just to explain the scale. And that raises the next question. If this star really is that large, why is it so hard to measure? And why does its size push so close to the limits of what stars should be able to become? But there is a problem with Stephenson 2-18. A star this large is not easy to measure, and it is not easy to explain. Because when we look at a star like the Sun, we are looking at something close, bright, stable, and well understood. We can measure its size with extreme precision. We know its distance, its brightness, its temperature, its mass, its behavior. But Stephenson 2-18 is completely different. It is far away, hidden behind dust, buried in a crowded region of the Milky Way, and surrounded by uncertainty. That makes everything harder, because scientists cannot simply fly toward it. They cannot place instruments beside it. They cannot measure it the way we measure nearby objects. They have to study the light that reaches us, light that has travelled across thousands of light years through clouds of dust and gas, before finally arriving at our telescopes. And by the time that light reaches Earth, it carries clues, but not simple answers. To estimate the size of a star like this, scientists need to understand how bright it truly is, how far away it is, how much dust is blocking its light, how hot its surface is, and how much energy it is releasing. Then they use models, calculations, and observations to estimate its radius. But if one of those pieces is uncertain, the final size can change. If the distance is slightly wrong, the brightness changes. If the dust is misunderstood, the true luminosity changes. If the temperature estimate shifts, the radius changes too. And with a star as extreme as Stephenson 2-18, even small uncertainties can become enormous. That is why the number sounds so dramatic, but also why it must be treated carefully. A radius around 2,150 times the Sun is astonishing, but it is not the same as measuring a planet with a clear surface. A red supergiant does not have a hard edge. Its outer layers are swollen, diffuse, unstable, and constantly changing. The surface is not like the surface of Earth. It is more like a vast atmosphere fading into space, a huge envelope of gas, expanding, pulsing, losing material, blended into the dust around it. So where does the star actually end, and where does the material around it begin? That question is not always simple, and that is what makes these giants so difficult. They are not neat objects. They are dying stars in motion, stars shedding parts of themselves into space, stars with outer layers so huge that they challenge the idea of a clean boundary. And Stephenson 2-18 may push that challenge even further, because if it really is as large as some estimates suggest, then it sits near the edge of what scientists expect red supergiants to become. A star can only expand so far before its outer layers become unstable, before radiation pressure, gravity, mass loss, and eternal changes begin to tear at its structure. At some point, a star this inflated may no longer be able to hold itself together in the same way. It may lose mass rapidly, surround itself with dust, and move closer to the final stages of its life. That is why Stephenson 2-18 feels almost impossible. Not because it breaks physics, but because it sits near the limits of our models, near the boundary between what we can confidently explain and what still makes scientists cautious. Maybe the star is truly that large. Maybe the estimate will be revised one day. Maybe future telescopes will sharpen the numbers and show us a clearer picture. But either way, Stephenson 2-18 remains extraordinary, because even the uncertainty tells us something important. The largest stars are not simple. They are distant, dusty, unstable, and difficult to define. They force scientists to combine observation with modelling, to correct for hidden dust, to measure light across different wavelengths, to compare what they see with what stellar physics predicts, and slowly, piece by piece, turn a faint object in the Milky Way into a star large enough to swallow the solar system past Saturn. That is the power of astronomy. We cannot touch Stephenson 2-18. We cannot visit it. We cannot see its surface up close. But by studying its light, its colour, its brightness, and the region around it, we can begin to understand something almost unimaginably far away. A star hidden in dust, a giant near the limits of size, a cosmic monster that may be showing us how extreme stars can become. But no star stays like this forever, and for a giant this massive, this unstable, and this far into its life, the ending may be even more violent than the size itself. A star like Stephenson 218 cannot last forever. Something this large, this unstable, this extreme, is not built for a quiet ending. The sun will live for billions of years, burning steadily, slowly changing, before eventually expanding into a red giant and fading into a white dwarf. But massive stars live differently. They burn faster, they shine harder, they consume their fuel at a terrifying rate, and because of that, their lives are much shorter. A star can be enormous, brilliant, powerful, and still be running out of time. That is the hidden truth behind red supergiants. They are not young, calm stars at the beginning of their lives. They are stars moving toward the end. Their outer layers have expanded, their cores have changed, their balance has weakened, and deep inside them, fusion is building heavier and heavier elements. Hydrogen becomes helium, helium becomes carbon, carbon can become oxygen, neon, magnesium, silicon, and eventually, in the most massive stars, iron begins to form in the core, and iron is different. For most of a star's life, fusion releases energy. That energy pushes outward, holding gravity back, keeping the star alive. But iron does not give the star the same support. Once the core becomes dominated by iron, the star is running out of options. Fusion can no longer easily save it. Gravity begins to win, the core collapses, and in a fraction of a moment, one of the most violent events in the universe begins: a supernova. The outer layers of the star are blasted into space. Material that once belonged to the giant is thrown outward at incredible speed. The star tears itself apart, and for a brief time, the explosion can shine brighter than entire galaxies. This may be the fate waiting for many red supergiants, a final collapse after millions of years of burning. A death so powerful that it does not simply destroy the star, it changes the space around it. Because when a massive star explodes, it spreads heavy elements into the universe, elements made in its core, and elements forged in the violence of the explosion itself: carbon, oxygen, silicon, iron, the ingredients that later become planets, moons, rock, metal, water, and life. That is the strange beauty of stars like Stephenson 218. They are terrifying because of their size, but important because of what they leave behind. A giant star dies, and its remains become part of the next generation of the universe. Dust clouds, new stars, new planets, maybe even future worlds where life can begin. The atoms inside our bodies were not made in empty space. They were forged in stars and scattered by ancient stellar deaths. So when we look at a monster like Stephenson 218, we are not only looking at destruction, we are looking at creation waiting to happen. A star so large it could swallow the solar system, one day giving its material back to the galaxy, feeding the darkness with the ingredients of future light. That is what makes its ending so powerful. It is not just the death of a star, it is the recycling of the universe, a cosmic explosion turning one impossible object into the raw material for things that may exist millions of years later, planets that have not formed yet, oceans that have not cooled yet, life that has not begun yet, and maybe civilizations that will one day look back into space and wonder where their atoms came from. Stephenson 218 may be one of the largest stars we have ever found, but even something that vast is temporary. Its size will not save it, its brightness will not save it, its power will not save it, because in the end, gravity always returns. The giant collapses, the outer layers erupt, and the star that once made the solar system feel small may vanish in a flash of light powerful enough to reshape everything around it, leaving behind either a dense stellar remnant, or perhaps, if the conditions are extreme enough, a black hole. And that is the final lesson of stars like this. The universe can build things almost too large to imagine, but it does not let them stay forever. It burns them brightly, uses them violently, and then scatters them back into the cosmos, so future stars, future planets, and future life can rise from the remains. The sun feels eternal, a constant fire in the sky, the center of our solar system, the source of almost everything Earth depends on. Its light warms our oceans, its gravity holds the planets in place, its presence defines day, night, seasons, time. To us, the sun feels like the greatest object in existence. But Stephenson 218 changes that feeling completely, because compared to a star like this, the sun becomes small, not weak, not unimportant, but small. A familiar star beside something almost beyond scale. Stephenson 2-18 may be large enough to contain billions of suns inside it. Large enough that if it replaced the sun, Mercury would disappear, Venus would disappear, Earth would disappear, Mars would disappear, Jupiter would disappear, and even Saturn would sit near the reach of its outer layers. The solar system itself becomes the comparison. Not Earth, not the sun, but the orbits of planets, distances that already feel impossible to us, reduced to a way of measuring one star, and that is what makes it so haunting. Stephenson 218 is not just a big object. It is a reminder that the universe operates on scales human instinct was never designed to understand. We live on a small planet, orbiting an ordinary star inside one galaxy among hundreds of billions, and somewhere in that same galaxy, hidden behind dust, there may be a star so large that our entire inner solar system would vanish inside it. But even this giant is temporary. Its size will not last forever. Its outer layers are unstable. Its life is moving toward an ending, and one day stars like this may collapse, explode, and scatter their material into space, destroying themselves, but also feeding the universe with the elements needed for future worlds. That is the strange truth of giant stars. They are monsters of scale, but also engines of creation. They burn violently, they die violently, and from their remains, new stars can form, planets can form, and eventually, life may appear. So Stephenson 218 is more than a record holder, more than a number, more than a star that makes the sun look tiny. It is a glimpse at the extremes of what nature can build. A star near the limits of size, a cosmic object so vast that it challenges measurement, and forces us to ask how large a star can truly become. Maybe future observations will change the numbers. Maybe another star will take its place. Maybe Stephenson 2-18 will one day be revised, or surpassed, but the meaning remains the same. The universe is capable of building things so enormous that even our solar system becomes small beside them. A star can be so large that worlds vanish inside its atmosphere, planetary orbits become swallowed, and the sun itself becomes only a tiny point of comparison. That is why Stephenson 2-18 matters, because it reminds us that the universe is not built around human scale. It is deeper, older, larger, and stranger than anything we are prepared for. And every time we think we have reached the limit, the biggest star, the widest distance, the darkest void, the universe shows us something even greater, something hidden in dust, waiting to be measured, waiting to be understood, and reminding us that even the things we think are enormous may only be small beside what is still out there,